In today's lecture, we are going to look at the noise and offset of the one-stage op-amp. So let us first draw the circuit of the one-stage op-amp that we've been looking at. So for this particular analysis, I'm going to assume that the current source at the bottom is ideal. So at the end, we'll see what happens if the current source also produces noise of its own. So the current source has some current, 2I0, and I'm going to number the transistors, input transistors M1 and M2, and these transistors, the PMOS load transistors, are M3 and M4. Now the way I'm going to approach this is I'm going to calculate the noise. I'm going to short circuit the output. So I'm going to short circuit the output to ground, and I'm going to calculate the short circuit noise current. So I'm going to call that ISCN square. Then I'm going to divide the short circuit noise current over the transconductance of the op-amp, which I'll denote by capital GM. And if I divide this by the square of the GM of the device, I will get the input referred noise voltage squared, which I will denote by EN squared. This is the input referred noise voltage of the op-amp. This is the same procedure we have used even for simpler circuits. This is very useful because op-amps in general are voltage controlled current sources, the CMOS op-amps that we are looking at. So now let us consider each noise source in turn. I have 4 noises. Let us assume that each transistor produces a noise which we'll denote with a subscript 1, 2, 3, 4. So I'm going to say that the total noise is the sum of the individual noise currents at the output, IN1 squared out, IN2 squared out, plus IN3 squared out, plus IN4 squared out, where each of these terms is the contribution of the corresponding transistor. And we'll take 1 or 2 of these, and then we'll generalize to the actual output noise current. So let us just take the noise of N1 alone. So let us say this is the noise of N1. Now the way I'm going to do this is I'm going to, as we know, the way we have approached this for noise is we have said that this is the same as having 2 current sources in series. As far as the nodes of interest in the network are concerned, it does not change. And moreover, you can also ground the central node. There is no current through the central node, and therefore there is no problem in connecting that to ground. This is exactly the strategy that we are going to adopt. So I'm going to take this and I'm going to split these into 2 current sources. I'm going to use 2 different colors. So for the top one, I'm going to use red, and for the bottom one, I'm going to use blue. and this center point is grounded. And so both of these are equal to IN1 squared. Now again, the corresponding currents in the circuit I am going to replace by the corresponding colors. So let us simply look at the blue colored values alone. So I have a current IN1 squared which is flowing out of this node, and at this point this current source IN1 squared sees two transistors M1 and M2. On both sides the input impedance is 1 over GM, and because you are looking into the source of the transistor, and therefore there is going to be a current through M1 of value IN1 squared over 2, and there is going to be a current through M2 of value IN1 squared over 2. Now what happens to this current on the left side? The current through M1 will flow through M3 to create a small signal voltage here, and that small signal voltage will also force a current through M4 equal to IN1 squared over 2. And if you apply KCL at this node, so now let me change this color so that there is no confusion. I'll change that to black so that there is no confusion. So as you can see, if you apply KCL at this node for this blue colored current, the noise current flowing through this side is 0, because M4 is pushing IN1 squared over 2 and M2 is absorbing IN1 squared over 2, so there is no noise current flowing due to the blue current source. What happens to the red current source IN1 squared? So let us now look at that. So if I look at this current, now this current is flowing into this node, and it turns out that this current is actually going to try to split between M1 and M3. Now as you can see, M1 presents an impedance looking down at its drain of RDS, whereas M3 presents an impedance which is 1 over GM3, and clearly 1 over GM3 is going to be a much lower impedance, and therefore this current is going to flow, most of the current is going to flow through this transistor. If that happens, then that current will automatically get mirrored into M4 also. There is no noise current through M2, and all of this current will flow into the short circuit at the output node. The direction of the current doesn't matter, because this is a noise current. You are only looking at the square of the noise current. It is only the noise power that matters. So clearly all of noise of M1 ends up at the output node. What about M2? As you can imagine, you will see the same effect for M2 also. You can analyze it and show that all of the noise of M2 also turns up at the output. Now let us quickly see what will happen for noise of M3. So to do that, I will create a copy of this on the next page so that we can analyze this separately. So now let us assume that M3 has some noise current, which is IN squared 3. Now what happens to this current? Clearly the VDD node is a small signal ground for noise analysis. Now this node At this node, the current IN3 tries to split in two directions, and you can clearly see this is very similar to the red color noise source that we just analyzed on the previous page. And you can see that all of this current would try to flow back into M3 itself. It would generate a small signal noise voltage here, and it would cause a current IN3 squared to flow here, and it will flow through the output. So there will be a current IN3 squared flowing into the output. And you can apply a same analogy for M4 also. Therefore, you can clearly see that this is IN3 squared and this is IN4 squared. So it turns out for this one stage op amp, all of this current M1, all of the noise currents of M1, M2, M3 and M4 will flow through the output. Therefore, the total short circuit noise current of the transistor is nothing but 8 kT by 3 into GM1 plus GM2 plus GM3 plus GM4, and if into delta F. And now if I am looking at the density, power density, spectral density, then this is 8 kT by 3 into the sum of all the GMs. Now this can be further simplified because the two parts are identical. I can now write it as 16 kT by 3 into GM1 plus GM3. So this is the short circuit noise produced by the one stage op amp. Now what is the overall transconductance of the op amp? So this is nothing but the short circuit current over the input applied voltage VD. That is clearly just GM1 of the input transistors. Therefore, the input referred noise voltage of the transistors is nothing but the short circuit noise current density squared, noise squared density over GM1 squared. So this is nothing but 16 kT by 3 GM1 into 1 plus GM3 by GM1. Now the important thing for us is to understand how to reduce noise, because that is going to be critical to maintain the SNR of the signal. Now as far as optimizing noise is concerned, so the first thing you need to minimize is, or first thing you need to do, clearly larger the value of GM1, lower will be the noise. It's clear that the input referred noise voltage squared, En squared, is nothing but is inversely proportional to it decreases as GM1 is increased. It is not just inversely proportional, there is some squared term also, but it's clear that as GM1 increases, the value of En squared will go down. Now the other thing you know is to minimize GM3 over GM1. So clearly, if you reduce the relative transconductance of M3 and M4 relative to M1 and M2, you will also reduce noise. That is also clear from the second term in the noise. Now, how do you reduce GM3? It turns out that to reduce GM3, you need to reduce either I0 or the width to length ratio of 3 and 4. I naught is of course the bias current of 3 and 4. Now this term also affects GM1 and many other parameters of the op-amp, so you would not prefer to do this, and therefore the only option is to reduce GM3. So if you decrease, the only option is to reduce the width to length ratio of 3. Now if you keep the current constant, and reduce the width over length, it turns out that the overdrive voltage of the PMOS transistors will start increasing. So in this particular design, you want to maximize the overdrive voltage of M3 and M4. That would give you best noise performance. Now what about offsets? It turns out that you can use the same technique, you can use the same type of analysis to analyze offset also, and what we are going to do is we are going to simplify our analysis of offset. We are going to follow the exact same procedure. We are going to assume some mismatch, and we are going to look at the offset current, short circuit offset current flowing through the output. So we are interested in offset current flowing through the output, and we will apply mismatch to different portions of the circuit and calculate the offset current. We will divide it by the transconductance squared to get the sigma squared of the offset at the input. So now the dominant sources will be considered. So these are Vt of 1 and 2, the threshold voltage mismatch between 1 and 2, and the threshold voltage mismatch between 3 and 4. These are the two dominant sources of offset in this circuit, and this is what we are going to consider for this particular analysis. So let us assume that there is a delta Vt3 mismatch between 3 and 4, and there is a delta Vt1 mismatch between transistors 1 and 2. In other words, transistor M1 may have a voltage of threshold voltage of delta V of Vt1. M2 will have a threshold voltage of Vt1 plus delta Vt1. So if you do this, you can clearly show that if you connect the inputs to ground, you will see that if the threshold voltages are not equal, there will be an offset current flowing through the short circuit, and it turns out that and let's call that delta ISC off, and this value of offset current is clearly going to be GM1 times delta Vt1 plus GM3 times delta Vt3. That is purely because a difference in offset voltage between M1 and M2, okay, the offset voltage delta Vt1 can be considered a small increment on top of the bias point, and same thing with M3 and M4, and therefore you can write the difference in the currents between M1 M2 as GM1 times delta Vt1. The difference in currents between M3 and M4 is GM3 times delta Vt3, and clearly both of these, the sum of these two, will flow through the output short circuit. Now therefore you can now write the sigma squared, offset at the input is clearly GM1 squared sigma squared Vt1 squared plus GM3 squared sigma squared Vt3 squared over the transconductance squared, which is GM1 squared. Therefore, the input referred offset sigma squared is nothing but sigma squared VT1 squared plus GM3 over GM1 squared times sigma squared VT3 squared. Now, if you want to minimize the input referred offset, we again know what to do. We need to maximize GM3, we need to minimize GM3 and maximize GM1 so that this term goes to 0. Now you can see this term becomes negligible. You can see that the offset voltage of the input pair appears directly as an input referred offset voltage. That is very important to note. The offset of the input pair M1 and M2 appears directly at the input as an input referred offset. There is not much you can do about it except to reduce sigma squared VT1 squared itself.